Ladies and gentlemen, today we'd like to discuss why we need a 2D, 2.5D, up to 3D sequence stacking and advanced packaging technologies in TSMC 3DFabric for interconnect. Here is the TSMC 3DFabric website, and you can find their release information as your reference. TSMC's goal of the 3DFabric is to offer their customers flexibility in product design, to bring packaging technologies to the forefront for innovation, and to improve the product's performance, function, and cost. I will try my best to connect those images clearly. As usual, the first one is energy efficiency. From ISCC summary trends, it's clear that we must control the churn loss at 9 rate much less than 3 dB to achieve the energy efficiency to be less than 0.2 picojoule per bit, which is our target. This will end up 200 milliwatt for the data transfer of 1 terabit per second. Also, please keep in mind, to make the loss little at the 9 rate, we must also reduce the 9 rate, which means the line rate is decreased as we discussed in the Why Not a High-Speed series. Do you know why we must apply for such a huge data transfer of 1 terabit per second or even higher? Think about the data exchange images for 5 seconds. Correct. Not all the data information is within just one chip. Otherwise, the chip size would be too big to fabricate reliably in a high yield or to operate properly. Therefore, people start to come up with multi-core CPU and GPU ideas since 2000. 10 years later, people may apply this multi-chip MCM to other chips, and is also called System in Package SIP. Another 10 years, from ICC trend in number of the MCM will even grow rapidly owing to the improvement of the package technology. In addition to the packaging technology, what's the motivation to push the rapid growth? Bingo! Time is money. The MCM can shorten the time to market since people can reuse their existing circuit blocks in the old technology that don't need to migrate or port their design frequently to the new process node. Those MCM helps other faster innovation instead of wasting the design resource in the design porting and delaying the product cycles. Another benefit from the design cycle is the low cost. Similarly, people can reuse blocks such as analog I/O, RF, and those that do not change frequently nor scale well on a more mature or low-cost process node. They then can focus on the logic design and scale well on foundry, most advanced semiconductor technologies. For example, we can utilize their new DSP design in the 3nm chip, but keep our old series I/O design in the 28nm to save the cost and achieve the best performance in 3nm digital and 28nm analog blocks respectively. So, obviously, those digital and analog signals must be passed properly with little power overhead. If the MCM idea is simple and looks promising, why did not apply extensive 20 years ago? Good question. the initial 2D MCM was low cost in the earliest form, which typically rely on wire bonding. Therefore, both the line rate and number of lanes is limited. The goal of the MCM is to speed complex functionality across multi-chips, which may require a high throughput. So, having a new free chip BGA will help the high line rate owing to the better signal integrity with the slightly increased number of lanes. So, we are still limited by the density due to the coarse bond pitch, roughly 140 micrometer, and large trace dimension. How can we improve the data transfer with the 2D MCM? Yes, to increase the throughput, we must increase the line rate. Unfortunately, we mentioned several times, the higher data rate will result in a more insertion loss and is more sensitive to impedance discontinuity. Therefore, even though the free chip BGA can reduce the loss, reflection, crosstalk, etc., as I issue, those impairments will still degrade the performance at a very high data rate. Not to mention, the power will go up a lot. So, what can we do? Yes, we must provide the smaller bond pitch, roughly 40 micrometer, and finer trace dimension, such that the number of lanes can be increased. That was the motivation of the 2.5D packaging structure, which allows two or more active semiconductor chips are pressed side by side on a second interposer for achieving extremely high die-to-die interconnect density. Since the bandwidth density is increased through enabling the massive scalable pairings, the line rate can be reduced a lot. Then the insertion loss and reflection will not be a concern anymore, even though the RC dominant wires in the second interposer has a significant insertion loss. Can we do better than the 2.5D packaging? Of course, in a 2D structure, two or more active semiconductor chips are pressed side by side on a second interposer to achieve extremely high die-to-die interconnect density. In 3D structure, through a vertical dimension, the chips are integrated by die stacking for the shortest interconnect and smallest packaging footprint. The most application of the 3D stacking is applied in the HBM memory system, since the stacking structure not only removes the low C RC dominant channel in the 2.5D, but also shorten the high-speed channel with less loading. The loss is very little and the power efficiency improves. So overall, the signal integrity was very good. But do you see another issue in the 3D stacking? Right, thermal could be a concern, even though TSMC or other companies are trying to improve it. Intuitively, the higher density will lead to the higher thermal resistance, so this introduces to the thermal dissipation, power delivery, and power integrity PI issue. Although those items will be the new challenge in the 3D stacking, the 3D packaging technology does add the flexibility in product design to shorten the time to market, bring the system design innovation, enhance the performance, functionality, and low cost, low power. Here are the summarized images of why we need TSMC 3DFabric for interconnect. As we discussed, we cannot put all the functionality in a single chip. Otherwise, the chip would be too big to fabricate reliability in a high yield. Therefore, we must divide the chip into multi-chip module MCM. In addition, we can reduce the time to market and cost at the same time if we apply a different kind of functionality in different technology. For example, we can utilize the new DSP design in the 3nm chip, but keep our old SerDes I/O design in the 20nm to save the cost and achieve the best performance in 3nm digital and 20nm analog blocks, respectively. So those digital and analog signals must be communicated properly with little power overhead. Unfortunately, the MCM in 2D packaging needs a higher data rate to keep the same throughput bandwidth due to the low density in the packaging. Then 2.5D would have a higher density in the package such that we could lower the data rate to get the better SI performance and low power. With 3D stacking, the interconnect is even shorter and more dense with a very good SI, but adds the PI concern due to the thermal issue in the high density, which I believe should be better over time. So overall, the 3DFabric for interconnect does add the flexibility in product design to shorten the time to market, bring the system design innovation, enhance the performance, functionality, and low cost, low power. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.